last talk. We're very happy to have Andrew Putman from Rice, and he will tell us about. Good job. See?
You're just setting the mood for the last time.
Modular symbols, class numbers, and the top-dimensional cohomology of SLNOK.
Okay, well, thank you very much. This has been a tremendous pleasure to be here. And since it's the last talk of the conference, it's my pleasure to ask for a round of applause for your organizers.
And for our cinematographer.
Yeah, and for the cinematographer.
She's going to make it.
That's right. Yeah. Anyway, yeah, this has been a really fun conference. So I grew up in Atlanta, and it's just been a pleasure to be back here, you know, to see the hills and the trees and stuff. You know, this is the first time I've been in Athens, and you know, since I was an adolescent, so you know, probably this is a very different experience. So what I want to talk about today is joint work. This is joint work with Tom Church and Benson Farb. So we've had a lot of talks in this conference about the mapping class group of a surface. We've had a lot of talks about the automorphism group of a free group. So there's a sort of holy trinity of groups in geometric group theory, and one is conspicuously missing, and that's the arithmetic groups. And so I want to give a talk that's sort of close off the conference to make sure that happens. So in this talk, so I guess I'll begin by introducing some notation. So O, that's going to be the ring of integers. So in an algebraic number field, which I'm going to call K. So if, you know, I'm not going to sort of use any serious algebraic number theory during the talk. I'll sort of hide all that. So you can just sort of think of sort of the easiest possible examples. You know, for instance, Z, the Gaussian integers, Z adjoint I. You know, maybe you add a something quadratic, so Z adjoin root 2, for instance, etc. So just think about things like that. So the group I want to be talking about is SLN over this ring of integers. So this group SL in O, this is a lattice in a Lie group, so G. And so just in case you haven't seen this before, let me give you a couple examples here. Some of them are pretty obvious. So for instance, SL in Z, that right there is a lattice inside SL and R. Okay, that's no surprise. We do the Gaussian integers. We take SL in Z adjoin I. Well, that's of course inside SL in C. How about our last example, though? Well, you might think, so SL in Z adjoin the square root of 2, well, it's definitely contained inside SL in R. But it's not a lattice in there because it's not discrete. In fact, the Z adjoin root 2, that's not even a discrete subgroup of R. So there's just no hope in the world for that. And so the trick is you embed it actually in the product of SL in R cross SL in R. How do you do that? What you do is you take a matrix M, which should be a capital M, I suppose. You can't erase markers with your fingers. So M, and you map that to the product of M and sigma of M, where what is sigma? Well, sigma right there is the element, the generator of the Galois group. So it's sigma of, so A plus B root 2 is equal to A minus B root 2. And this makes this discrete, and it's so it's sort of easy to see it's discrete, and being a lattice means it also has finite covolume. That's a more subtle fact. I don't know who to attribute to it. If in the most general possible situation, it's to Borel and Hari-Chandra, but this is for these kinds of groups, this is probably much more classical. Okay, so we have these lattices in these Lie groups. So how do we introduce geometry into this situation? Well, so this implies that there's a nice manifold upon which these groups act. Well, G itself is a manifold. Of course, SL and O acts on this Lie group G. But G has a lot of topology. G is not contractible or anything. So to do that, where's all the topology inside G living? Well, G deformation retracts onto its maximal compact subgroup. And so therefore, this group, so SL in O, this acts, so I guess it's properly discontinuously on its G modulo its maximal compact subgroup. So this is what's called a symmetric space. So some of these are very familiar. For instance, SL2R, you know, that the associated symmetric space would be hyperbolic space, hyperbolic 2 space. SL2C, well, that's the isometry group of hyperbolic 3 space. And so you can view these as sort of higher dimensional, more complicated generalizations of hyperbolic 2 space or hyperbolic 3 space. For SL2Z adjoint root 2, you'd have H2 cross H2 would be the symmetric space. And so this right here is a beautiful space. It's contractible. So it has a metric of non-positive curvature. It has many other properties. It's one of the most beautiful types of spaces in mathematics. And in fact, a lot of type-Muller theory and whatnot was developed sort of by analogy with these spaces. So when I talk about them, I'm going to do the opposite of the historical order. The historical order would be to develop type-Muller theory to motivate everything by analogy with this, but I'm going to go the other way around. I'm going to try to discuss this space and explain what the analogous things are in type-Muller theory. Okay, so what do I want to talk about in this talk? The sort of theme of this talk is the cohomology of these groups. And so what's the sort of basic facts here? Well, so you know, these groups right here, they have k-pi1s, or they almost have k-pi1s, which you just take this G mod k, it's a contractible space, you mod out by SL and L. Okay, so that's some finite dimensional manifold. And so so what we're really trying to understand is the cohomology of that manifold right there. So the first basic fact is a theorem of Borel from 1973. And so he calculated, so the cohomology HI of SL in O with Q coefficients, everything I'm going to say today is going to be rational. So in what's called the stable range, which means in S, this is when N is very large compared to I. Okay, so you look at, say, H1, and you let N get bigger and bigger, and eventually it settles down. In fact, H1 for SL and O is going to be 0, as once N is at least 3. So this is calculated. The cohomology of the stable range has been understood since the 70s. Other than that, outside the stable range, very little is known. There's a bunch of sporadic calculations that have been done by number theorists, people working automorphic forms and whatnot, but there are very few systematic calculations. And so what I want to talk about today is sort of the opposite of Borel's theorem. So Borel is when N is very large compared to I want to look at the very top degree where there could be any cohomology whatsoever. Okay? And so what do I mean by that? Well, so let's let nu, right there, that's going to be the virtual cohomological dimension. Let me put the word virtual in parentheses. So the dimension of SL in O. Okay, the word virtual is there because these things have torsion. So they don't actually act freely on G mod K, the same way the mapping class group doesn't act freely on type-Muller space, but the only problem is some finite groups. And so if you ignore those finite groups and restrict yourself to doing rational calculations, the cohomological dimension is finite. Okay, just because these are the fundamental groups of, basically, of finite dimensional aspherical manifolds. So that's less than infinity. You can write down a formula for it, so e.g., so if, so I guess not if, but for, so SL in Z, we have that mu would be equal to, you can do a little calculation, n choose 2. Okay, and you can write down a formula in general just from the basic, the number of real and complex embeddings of your ring of integers. So the theorems I want to talk about are what happens in this virtual cohomological dimension. So I'm going to state two theorems right now, there's going to be a few undefined words in them, and I'm going to define the words after that. So we have two sort of contrasting theorems here. What they do is they sort of relate the arithmetic properties of this ring of integers to this top-dimensional cohomology group. So theorem 1 says that the dimension, so of, you take this top-dimensional cohomology group of SL in O with Q coefficients. So it says this has to be large. And what do I mean by large here? Well, this is greater than or equal to, and then there's going to be some quantity here which is associated with the arithmetic of our ring of integers called the class group. Well, you take the number of elements inside the class group. I'll say more about, if you don't know what that is, I'll say more about that later. Okay, I'll actually give a definition of it later on, which has some geometric content. So, but you take that right there, minus 1, and raise that to the n minus 2 power. Okay, so if the arithmetic of our ring of integers is complicated, there's a huge amount of cohomology in this top degree. Okay? So that's the first theorem. And so now, of course, this theorem has, if the class, this thing right here, the class group is a finite abelian group. So if it's 0, so if the class number is 1, the number of elements in it's 1, this theorem tells you nothing, right? It says the dimensions at most is 0. So that's maybe less interesting. I guess this is for, this is for n at least 2, but that's maybe sort of implicit in the way it's phrased. So theorem 2 is a sort of partial converse. It says what happens if the class number is 1. And there we unfortunately have to put some conditions. So theorem 2. So let's assume that O, so is either, so it's Euclidean, so it has a Euclidean algorithm, or it has a real embedding. So, or O, we'll say, is contained inside the real numbers. So also, so assume that the class group CL of O, I'll say the class number is equal to 1. So the number of elements inside the class group. And then the conclusion right there is that this top-dimensional cohomology group, H mu of SL in O with Q coefficients is equal to 0. So for instance, for Z, it says the top-dimensional cohomology group is equal to 0. And that result was known, so let me make a remark. So for O is equal to Z, so this is a theorem of Ronnie Lee and Sharva from the late 70s. Okay, so I want to discuss these two theorems. This is going to be the theme of this time. So,
can I ask some basic questions before I get lost?
Yeah.
Okay, so virtual cohomological dimension. I thought it was, what is cohomological? Hey, what is cohomological dimension?
So cohomological dimension. So if you have say a group, the cohomological dimension, or let's say you have some space. The cohomological dimension would be the top degree in which there exists some non-zero cohomology with respect to some local coefficient system.
I see that. So being 0 doesn't. I mean, I was worried.
That's right. Yeah, exactly. Yeah. So,
Okay.
so that was what I was going to say next. You might think, what the heck?
Yeah.
Why is this thing 0 if this
Right.
is the cohomology dimension? The point is that it's going to be non-zero with respect to some local coefficient system, but not with respect to the trivial one.
I see.
Necessarily. And this is actually a basic phenomenon. I don't think I'm going to. I said in the abstract I talked about analogous results for the mapping class group too. I don't think I'll have much time to talk about them, but let me just can say verbally. Theorem 2, Church and Farb and I also proved a result like this for the mapping class group, that the top-dimensional cohomology group of the mapping class group is also 0 rationally. And it's the same thing. The cohomological dimension, I think it's like 3g minus 4. You have to write down. You can sit down and write out a formula and figure out what the answer should be. But what the dimension is. So, and I guess for the automorphism group of a free group, this is a big open question. I don't know. I sort of probably would guess that the top-dimensional cohomology group is 0, but I'm not totally sure.
Okay, so my other question is kind of like feel for what this is saying. I mean, if G mod K was actually a closed manifold,
Right.
then, you know.
Well, G mod K, you mean G mod K mod gamma is a closed manifold.
Oh.
But modulo are, so G mod K is like the universal cover.
Oh, I see, right.
Yeah.
Yeah, sorry, mod gamma, right.
Yeah.
Right. Then there wouldn't be anything interesting at the top.
That's right, yeah, the top degree
So
would
this
be
is like,
Z, right?
Right.
Yeah.
So this is sort of, it's telling us something about how.
That's right, how non-compact this is.
Compact,
That's
yeah.
right, and you'll see in a few minutes, I'm gonna discuss theorem 1. I'm gonna explain sort of what it means for n equals 2 and O is an imaginary quadratic thing. So which means that this will be a hyperbola 3 manifold in that case, and I'll explain how this is related to the geometry of that 3 manifold.
Thanks.
So okay, so I'm gonna do that, but before I can do that, I have to say something about what this class group is. I haven't defined that, and this is maybe not something that people have at the tip of their tongue. They're geometers. So this is a multimedia talk, so I'm going to use both kinds of chalkboards. So let's talk about the class group. Okay, so this right here, so the class group of O, this is a finite, so abelian group. And it measures, so the failure of the unique factorization. So instead, I'm not going to give a formal definition of it, but I want to give some examples. I want to give a sort of geometric result that tells you how big it is. So for example, the first basic fact about it is this class group CLO is equal to 0. So the trivial abelian group, if and only if O has unique factorization. And that's true if and only if, by the way, so O is a PID. Okay, so that's the first sort of bit of content to it. The next, though, so I want to give a definition of it that maybe at least looks sort of geometric. So here's a sort of fact, and you can take this as a definition for the rest of the talk. So, and that's that. Well, we're not the actual group structure is not going to play a role in the talk. The only thing that's going to play a role is the number of elements inside it. And so, the number of elements inside the class group of O, that right there, it turns out to be the number of orbits of SL2O. So on the, you take, so K squared and you projectivize it. So the space of lines, that P doesn't look very good. The space of lines inside K squared. Okay, it's the number of orbits. So let me give you, so let me explain this, this might seem like a mysterious, thing. What's the relationship between this and unique factorization? So what's one special case? Oh, one special case is when O is equal to Z. And there it should say that there's exactly one orbit. And so how does that relate to unique factorization? Well, consider some point, which I'll write in homogeneous coordinates. I'm really destroying chalk today. So AB, at some point inside P of Q squared. Okay, so now A and B here, they're going to be two rational numbers, not both 0, and we can scale them however we want. So without loss of generality, we have that A and B, well, first we can clear denominators and make them both integers. So, and after that we can cancel any common factors, and we have A and B integers, and so they're also relatively prime. You just cancel all the common factors. Okay? And so then, what does that imply? That implies that there exists some C and D integers such that CA plus DB is equal to 1, right? And so thus, what we see is that if we take, so this point AB, that right there is equal to, well, we just write down a matrix AB we want this matrix to have determinant 1, so we put a C there and a minus B there, times 1, 0, check. So everything, so the orbit of 1, 0, the orbit of the point which is in homogeneous coordinates 1, 0 contains every point, it contains A. And you see, the relevance of unique factorization is I had to do this thing about relatively prime right there. Okay, and so so you can sort of see that the failure of this proof to work sort of reflects the failure of unique factorization of holding your ring of integers. So I'll sort of close my discussion of what the class group is by, I should give you some example of a non-trivial class group, and so the standard example you give when you teach a first course algebraic number field, algebraic number theory, is that the class group take the easiest one that's something that's non-trivial is to take z adjoin the square root of -5. And that right there is equal to z modulo 2. And so what's the failure of unique factorization? Well, here we have 6. That's equal to 2 times 3, right? That's but that's also equal to 1 plus the square root of -5 times 1 minus the square root of -5. And these are two essentially different factorizations of 6. There's sort of, there's always an ambiguity up to multiplication by units, the same way you can always multiply by -1 for the integers, but these don't differ by units. These are genuinely different unique factorizations. Okay, so that's what this object is that we're sort of using to generate cohomology, is this class group, yes?
So in theorem 2, you're assuming it's Euclidean. Why do you also have to assume the class number is 1?
Oh no, so class number, so Euclidean implies class number, but it's either Euclidean or it's real.
Okay.
Or it has a real embedding.
Okay.
Yeah. So if it has a real embedding, the class number definitely does not need to be 1. Okay, so now what I want to discuss next is I want to discuss, so theorem 1 is classical in the case n equals 2. And I want to explain that in a very sort of situation which I think might resonate with some of the stuff in this conference. And so here is theorem 1. So n equals 2, and to make it more concrete, let's say that O is equal to the ring of integers, and Q adjoin the square root of -d square free. I didn't just write z adjoin square root of -d because sometimes it's a little bit bigger. So let me discuss. I was going to underline that, but maybe that would make. I'll just put a colon right here. Okay. So. Anyway, let's pin down what this is saying in that case. So here, what we have is that so SL2O, this is a lattice in SL2C, which is more or less the isometry group of hyperbolic 3 space. Okay, I should have a key there, but let's ignore that. So the associated, the locally symmetric space, our classifying space for SL2O, is the space X, which I'm going to define as hyperbolic 3 space modulo SL2O. So X is what's called an arithmetic hyperbolic 3 manifold. It's actually sort of an atypical example of an arithmetic hyperbolic 3 manifold. So in particular, it's not compact. So it's not compact. So its cohomological dimension of X. Well, if it was compact, it would be 3. Since it's not compact, it's 2. I guess it could be 1, but it's not, because it's finite volume. So, and I'm going to give you an element of H2 in a second. So now, what's the basic fact? What's the relationship between the geometry of this arithmetic hyperbolic 3 manifold and the arithmetic of O? Well, here it is. So is the number of cusps is equal to the class number. So the number of cusps of x is equal to the number of elements in this class group. Okay, so let me explain why that is. That's actually not hard given this proposition right here. Oh, I guess I was thinking I erased that board in lecture right here, but I guess I can't do that. So, thankfully now my two theorems will be up there for the entire lecture. So, where does this stuff come from? Well, what are the cusps? Where do they come from in this case? So the cusps, those are in bijection with the conjugacy classes of parabolic subgroups. So one possible parabolic subgroup, for instance, would be the strictly upper triangular matrices. But there's others. So so what is a parabolic subgroup in general? Well, that's going to be the stabilizer of a line. In this case, so let's see. So I guess it would be, I'll call it k squared. Okay. K here, of course, being this q adjoining square root of negative d. Okay, so therefore this right here, of course, is the same thing by this fact, like stated right there. This is the number. This is the orbits of the action of SL2O on projectionization of k squared, and of course that right there is equal. Is equal. The number of such orbits is equal to the class number. Okay, so that's where so we have all these cusps corresponding to the class group. And so how can I use these cusps to cook up elements of H2? Well, so what's the picture look like? So our manifold looks like this. So, it's got some cusps. And maybe it's got some topology in the middle. So let's say I choose two cusps. Say so C, here's one right there and there's one right there. I can take a line, a ray that goes from one cusp and exits another cusp. Okay, this is a bi-infinite ray. Let's say that. So let's call that C and C prime, and so we'll call this. We'll say tau of C prime. That right there is a ray from C to C prime. Now, this is an embedded real line. So it's dual. Well, so it doesn't define an element of homology exactly because it's not compact. But it does. You can do one of two things. Either you can chop off the cusps, and in which case this becomes a relative one cycle, or you can look at locally finite homology. So either way, so tau defines tau C prime is dual to an element of H2 of X. What do? You just take some surface inside this 3 manifold and you count the algebraic intersection number between that surface and this ray. Okay? And so in general, so what you do, so what I should be producing is the class number -1, that number of elements of cohomology. So that should be, by the way, actually, there's a typo. 2. But it really should be n minus 2 says I'm not getting anything. It should be n minus 1. So dual to the amount of H2. So if the cusps, are C1 up through Ck, so an element of dual to element, I'll give this guy a name, let's call it, I'll just put bracket tau C prime. So then these element tau of C1, C2 up through tau C1, Ck, these are linearly independent. Okay, so I fix some base cusp, and I just take a ray from that cusp to all the other cusps, and I get that, 1 minus the number of cusps, number of elements in cohomology that are linearly independent. So that's what this theorem says here. Sort of in the higher dimensional setting, you can't do something this simple-minded. By the way, this ray being dual to an element of H2, that's what's called a modular symbol. That's where the word modular symbol in the title comes from. So in higher dimensions, you can't do something quite this simple-minded, because in higher dimensions, or higher rank, actually, I guess is the right word, the cusps overlap. And so you can't just take rays connecting two cusps. It's sort of, you have to do something more subtle. And so that's, and that's good because I actually produce a lot more stuff. It becomes more and more stuff as it gets bigger and bigger and bigger. But in general, that is, somehow the cohomology we construct comes from more subtle analysis of the geometry of infinity. Okay. So that's what this says in this situation. So I now want to discuss somehow what that geometry of infinity looks like, and how you study it. So, and then we'll also will sort of show you where theorem 2 comes from. Okay. So how do you study the geometry of infinity? Well, if you're doing type-Euler theory,
wait, this is supposed to convince us that theorem 1 is true?
That theorem 1 is true, yes. Because
why is that the right number? Tau C1.
So K here, K is the class number.
Yeah.
Right?
Yeah.
And so I get the class number minus 1.
Oh, yeah.
Elements of cohomology.
There's that many linearly independent things, so the basis has to be.
So yeah. Okay. So let me now go back to the general situation. And so,
can I ask you a question?
Yeah, sure.
What about with different coefficients? I mean.
Oh, with like a twisted coefficient system or something? Yeah. So I don't know how to produce a non-zero cohomology if you have a twisted coefficient system, because sometimes it's 0. For instance, if I look at the representation on k to the n, all the cohomology groups are 0. So there's no sort of way to do that, even if the class number that doesn't depend on the class number.
Okay.
But so there is a version of theorem 2. There is a vanishing theorem for for arbitrary rational representations of SLN or GLN, and so how but there theorem 2 it works in general. If you want to have the vanishing theorem for non-twisted coefficients, you have to assume n is large compared to the highest weight. So, okay. Let's see here. So let's go back. What is the geometry of infinity? Well, what's the geometry of infinity of type-Euler space or moduli space? It's sort of combinatorialized or described by the complex of curves. And the complex of curves was originally introduced to model a much older result of Borel-Serre on these locally symmetric spaces. And so there, the role of the complex of curves is played by a building. So let me discuss that right here. So Tn of k, that right there is going to denote the Tietz building. For k to the n. And so what is that? What that is, this is the simplicial complex whose, so I guess it'll be k simplices our flags. So it should look like 0 is properly contained inside V0, which is properly contained inside all the way up through Vk, which is properly contained inside big K to the n. Okay? And so you attach them, you know, if you delete an element of the flag, you get a smaller flag. So that's how you attach the cells to each other. Okay, so this measures, you should think of this as like the curve complex for these groups. I mean, really, the curve complex is like the Tietz building for the mapping class group. So this measures, so the geometry at infinity of this space, you know, we have our G mod K modulo SL in O. Okay? So now, what do we know about this? Well, what we know, the sort of basic result here is what's called the Solomon-Tietz theorem.
Are those K's different?
Yeah, one's uppercase and one's lowercase.
Oh.
That K, oh gosh, yeah, that K is the maximal compact subgroup. That K is the
field.
The field. I'm sorry, I can't change this now. But I'll never mention this K again, so that makes you feel better. If I could, I'd make it like fractal or something. But let's see. So what does the Solomon-Tietz theorem say? Well, what's the dimension of this Tietz building? The dimension is, well, the max, so it would be the 1 minus the number of elements in a maximal flag, right? So it's, the maximal flag has n minus 1 elements in it, because they're proper non-zero subspaces. And so therefore, the dimension is n minus 2. The Solomon-Tietz theorem says that it's n minus 3 connected. So it's 1 less connected in its dimension. So, and what that, another way of saying that is that this space T n of K, this right there is homotopy equivalent to a wedge of the top dimension, which is n minus 2 spheres. Okay? And so it has exactly one non-zero cohomology, reduced cohomology group. And so that's what's called the Steinberg module. So definition. So the Steinberg module is, and so my notation is going to be Stn of K, and we take the n minus second homology group of this, except we want reduced homology of this Tietz building. So say with, integer coefficients. Okay, so it's clear that the group SL, SLN, that SLNK, so acts on this Steinberg module. Okay, just because SLNK acts on the Tietz building in the obvious way. And so therefore we get an action at SLNO on there. Okay, so now that's the Steinberg module. So I said that this has something to do with the geometry at infinity. Okay, so what sort of the topological content of that. So if this were if this locally symmetric space were a compact manifold, then it would satisfy Poincare duality. So it's not compact. It has cusps. It has stuff going on in infinity. But let's see, if you chopped off those cusps, then you would get a manifold with boundary. And so manifolds with boundary, of course, also satisfy Poincare duality. They satisfy Poincare-Lefschetz duality. So it's got to be homology relative to the boundary. And so therefore, in the world of groups, you have to have some version of Poincare duality for the group cohomology of SLNO. But that duality has to take into account what's going on in infinity. And so that's what we have here. This is called Geary-Ekman duality. So this is Barreau and Serre. Let's see. So I guess Barreau and Serre. They showed that S L N O has we'll call it very equiduality. And what does that mean? Well, it's going to look sort of like Poincare duality. So, and this is rational. There's like issues with torsion as always. So let's say we look at the codimension I cohomology of SLNO with Q coefficients. That right there is equal to the ith homology of SLNO. But we can't just put Q coefficients there. We have to put Q tensored with this Steinberg module. Right there. So it's a twisted homology. It's homology with respect to a local coefficient system given by the Steinberg module. So this is the contribution from the boundary. This is why this is the group theoretic version of homology relative to the boundary. Okay. So what this says is that if you want to understand what's going on in the top degree, you're looking at where I is equal to 0. And so we're looking at 0th homology of something. And so what does that look like? So in particular, we have that H mu of SLNO right there with Q coefficients. That right there is H0 of SLNO with coefficients. I'm going to avoid having to write this over and over and over again, I'm just going to write Q here and tensor with Q in my definition. That'll simplify my definition. Otherwise I'll have to write Q tensored with this over and over and over and over again. So that's sort of annoying. So with coefficients in the Steinberg module, STN, and it should be a K there, actually. Okay, so what does this look like? So this right here, so if you take H0 of a group acting on some vector space, what you get is what are called the coinvariants of the action. So this right here, I'll write this down. So this is SPN of K, and you take the coinvariance of SLNO. Okay, so what does this mean? So this is equal, so like this, I'll write this sort of more generally. So if M is a G module for some group G, so M sub G is equal to M modulo the thing spanned by little m minus G of little m, such that little m is inside M and little g is inside G. Well, it is like somehow at the bottom and the top of the board you can't write them properly. It's like they've been cleaned to something. So they stay clean. Okay. So what we're doing is we're killing off the action. Okay, that's what H0 of a group with some local coefficient system is. Okay, so we need to understand what this these covariants are. So what I'm going to so to understand that, sure I'm doing okay for time. I am doing exactly how I said I would do for time. It's in my notes. I have 15 minutes remaining. So to do that, I want to. So the Solomon-Teets theorem actually says a little bit more than this. Okay, it also tells you what these spheres are, and so that's what I want to discuss now. So we can sort of see what the work that has to be done is. So these are what are called apartments. So let's let L be a frame. For k to the n. So what do I mean by that? What I mean is it's going to be an ordered set L1 up through Ln with k to the n equal the direct sum of L1 plus all the way up through Ln. So each of these L sub i's is a line. Okay? So these guys right here, these are lines in k to the n. Okay, out of these lines, I'm going to produce a sphere inside the Tietz building. Okay, so we then have an apartment. So which I'm going to call A sub L, and that's going to be inside. Well, it's going to be inside the Steinberg module. So that's going to be reduced homology dimension n minus 2 of this Tietz building. Okay, and so let me draw a picture of this so you can see it. So this is, I'm going to draw a picture for n equals 3, and then you'll see the general pattern. So it's going to be a sphere. So let's see. So n equals 3. So I want to get a sphere. So I want to get a 3 minus 2. So I want to get a 1 sphere, a circle inside this Tietz building. And so what do I do? Well, draw myself a little triangle like that. And I stick these lines, our L1, L2, and L3 on the 3 vertices. And so then, remember, the simplices are given by flags, right? So what I'm going to do then is I'm going to take, so in the middle of these guys, I'm going to stick the spans. So let's say that's the span of L1 and L3. There's going to be the span of L2 and L3, and there's going to be the span of L1 and L2. And you see, each of these lines, there's a flag associated to it. In this case, it's the L is contained in L1 and L2. L2 is contained in L1 and L2, etc. And I can't fill in the middle because that would be the span of all 3 of them, which is the whole space. And these are proper subspaces. And so you can sort of see what's going on in general. In general, you take a simplex of the appropriate dimension, stick each of these lines on the vertices, and then take the barycentric subdivision and just take spans. You fill in as you need to. Okay? So that's what an apartment is. These are the sort of natural spheres living inside this building. Okay, so what does the Solomon-Tietz theorem say? So Solomon-Tietz prime this says that the homology of this building is generated by these apartment classes. So it says that. So the homology of the building would be the right, like this is the Steinberg module H n minus 2 of this Tietz building. So the Steinberg module, this is spanned by apartments. Okay, that's great. So it says that if I want to calculate these co-invariants, I need to just show how to kill off any given apartment. Now that's not as easy as you might think. So I'm going to make the observation. So it's clear that SL in K, this acts transitively. On the apartments. You can take one decomposition, L1 through Ln of K to the n, to another one by an element of SL in K. So the SL in O action is very complicated. So you just try to give me an idea of how complicated it is, think about just O equals Z. you're trying to understand what are the orbits of SL and Z on basically direct sum decompositions of this Q to the n. That's pretty complicated. There's a determinant that gets in the way, but then there's other things too that get in the way. The orbits are they're not so easy to deal with. Okay. And for other rings of integers, things are even worse. So this, at this point you think, well, what can I do? And so what we do is we specialize. We don't just look at any apartments right here. We specialize to apartments where we can understand the SL and O action. So here's a definition. So let's say that L is equal to, so L1 up through Ln. This is a frame for k to the n. So then, so A sub L is an integral apartment. So if, well, we take O to the n, and we want that to be the direct sum decomposition of, well, we take L1 intersect O to the n, that's some O module, right? Some subspace of O to the n. We want that to be a direct sum decomposition up through, so Ln intersect O to the n. So not every apartment is integral. These are ones that correspond to, to direct. So it's much harder for say lines to Fastley's property. Let me show you an example of a non-integral apartment. So let's say that we're looking at the apartment. So if L is equal to, I'm going to work over Z. So we're going to take the span of the vectors. I guess it should be 2, 1. So that span, and then the span of the vector 0, 1. So then A sub L is not, so an integral apartment. So I guess it should be Q squared. Okay? So that's the sort of thing that goes wrong there. So what's our main theorem is that under the assumptions of theorem 2, the Steinberg module is generated by these integral apartments. So the theorem.
Oh, and that's a one that acts transitively.
Yeah. SL and O acts transitively on these integral apartments. That's right. Yeah. So it says that. So let's assume. So I guess we'll say the same conditions as theorem 2. So either Euclidean or contained in R in class number 1. So then, so SP in K is spanned by integral apartments. Now I should make a remark that the class number, so where does this class number 1 assumption come into play here? So so the class number 1, that implies that as, so an O module, we have that we take, so L intersect O to the n is isomorphic to O for all lines inside K to the n. Okay, so this is sort of where that assumption comes into in improving this theorem. In general, this L intersect O to the n is going to be some projective module, but not all. But sort of the class number also, the class group also classifies projective modules.
Sure, L integral.
This is for L any line.
Oh, okay.
So this is just for a line. Yeah. It's isomorphic. Yeah. And so so for any line, this holds. So and in fact, you can prove that this theorem is false if the class number is positive. So we prove that. So make another theorem, another remark. So this theorem is due to Abner, Ash, and Lee Rudolph if O is Euclidean. It's proved, I think, in 1976. CLI. But our proof is actually pretty different from theirs, even in the Euclidean case. Okay, so let me close. I think I should have like a minute. 3 minutes. Okay, great. So let me close by showing why this theorem implies theorem 2. So here is the proof of theorem 2. So it's enough to show that A sub L is so it's equal to, I'll write like this, is equal to 0 in the coinvariance STN K SL in O for an integral apartment. So A sub L, and this equals, is in the covariance is what I mean. Okay, that's what we have to kill off these integral apartments, and so I claim that's really, really easy. Why is that? Well, let's write, so L, we'll set it in lines, L1 up through Ln. Okay? And it's ordered. But it's actually, the order isn't the important thing, the orientation is the important thing. So if you purchase these LIs, all you're doing is changing the orientation of the apartment. So let's let L sub I, or I mean not L sub I, L prime, that right there is you just flip L1 and L2. So this is L2, L1, L3, up through Ln. So then, so A sub L and A sub L prime have opposite orientation. So A sub L is equal to negative A sub L prime, like in the Steinberg module. I haven't passed the covariance yet. However, so there exists some element M inside S ln O such that, so M L1 is equal to L2, M of L2 is equal to L1, and M of Li is equal to Li for I at least 3. So this uses the fact that they're integral. What I have to do is, well, what happens here, so you've got your direct sum decomposition, so we have two different direct sum decompositions of O to the n. So O to the n, that right there is equal to, well, it's L1 intersect O to the n plus, so L2 intersect O to the n plus all the way up through Ln intersect O to the n. That's great. So these guys right here are isomorphic O modules. They're both O, right? And so therefore, if I flip them, those are two different, I can have an isomorphism of O to the n as an O to the n module that takes this to this and this to this. That might not have determinant 1, but then I can just, these are lines. I can just multiply by a unit to make it have determinant 1. So, for instance, -1 will do the job. This thing right here will generally have determinant -1. We just scale it, and so therefore we're done. So the conclusion then is that, so A sub L is actually equal to A sub L prime. So A sub L is equal to 0. And I'm done. Okay, so I think I'll stop there.